Hi, everybody. I think this is our 22nd lecture for this class. And we left off kind of hurriedly last time with the Bolzano-Weierstrass theorem, but we did prove it. It was a short proof. And today I'm going to start by writing it up and then using it to prove something else. Okay? So let's recall what the Bolzano-Weierstrass theorem says. This is the following. What's it say? It says every bounded sequence has what?
Convergent subsequence.
That's right. That's what we left off with. So we're talking about subsequences here over the last few class meetings. And the reason that this particular fact was true, if you think back to it, was that if you give me a bounded sequence, what we learn, not only just any bounded sequence, but what we learn for any sequence, it has a sequence that is a monotone. It has a subsequence that's monotonic. So if you give me a bounded sequence, I can find a monotonic sequence within it, subsequence within it. And that monotonic subsequence, being part of a bounded sequence, will be bounded itself. And so what we have is a subsequence, which is a sequence, which is monotonic and bounded. And that means it converges by the monotonic convergence theorem. So that's the way the proof went. Well, one of the things that helps us get is a theorem which helps us prove, if we wanted to, the divergence criteria. I just listed the divergence criteria which we could have proven from previous facts, but we could really extend the divergence criteria to be an if and only if statement based on this fact that I'm about to write, which is based on the Bolzano-Weierstrass theorem. So here's a theorem. So this is new. It says, let x of n be a bounded sequence such that and let x be an element of R. Have the property that every convergent subsequence of x of n converges to x. Then what will happen is that x of n itself converges to x. Converges to x. Let me give you a second to write that down. We want to prove that. So what is it that we want to prove? We want to prove that if you give me some bounded sequence, and it's a sequence that there's this number x out there, such that every convergent subsequence of our sequence converges to that number x, then what has to happen is the original sequence, the parent sequence, has to converge to x. Okay, let's see how the proof of that goes. So the proof's going to be by contradiction. So how do proofs by contradiction go? Well, they go this way. We assume the if part, and we assume the opposite of what we want to show. And then we hope to get a statement that's silly, meaning that our assumption of the opposite of the conclusion must have been false. So it must have been wrong. So we end up getting the theorem that way. So here I'm going to let x of n be a bounded sequence. And let x be a real number such that every convergent subsequence of x of n converges to x. Now what we want to show is that x of n itself has to converge to x. What we're assuming is just that every convergent subsequence of x of n converges to x. So we want to show x of n converges to x. And we're going to do this by contradiction, so we're going to assume the opposite. We're going to suppose that x of n doesn't converge to x. It's not converge to x. Okay. So we had a fact. It was a fact about equivalence between statements. And one of the statements was you got a sequence that doesn't converge to x. Remember, there were three things in this fact. You know what I'm talking about? We ended up proving it over 2 days, and one of the days was, I think, last time. But we just proved this fact I'm about to use. So if x of n doesn't converge to x, there were three things that could be said. One of them, or two other things that could be said. One of which was, hey, there's some epsilon naught greater than 0 and a subsequence. Okay? So by a previous fact, there exists an epsilon naught greater than 0 and a subsequence let's say x of n sub k of x of n such that the absolute value of x of n sub k minus x will be greater than or equal to epsilon naught, and that's true for all k and other natural numbers. That's that previous fact we had last time. Now, this means that x of n sub k doesn't converge to x. No, that's okay. That's not a contradiction. Maybe that subsequence doesn't converge at all. But one thing I'm assuming, let's remember what we're assuming about x of n itself. It's a what kind of sequence? Bounded. That's right, Megan. It's bounded. And that means that the subsequence x of n sub k is also bounded. Okay? So since x of n is bounded, then the subsequence x of n sub k is also bounded. So let's concentrate on that x of n sub k for a second. It's a sequence, even though it's a subsequence, it's a sequence that's bounded. Okay? Well, the Bolzano-Weierstrass theorem tells us that every bounded sequence has a convergent subsequence. So I'm talking about x of n sub k. It has a convergent subsequence. And I'll write it down this way. So that's right, Calvin. Balzano, Weierstrass. Theorem. X sub n sub k has a convergent subsequence. Let's call it, be careful, X sub n sub k sub r. R is running. Okay? So I'm talking about a subsequence of X sub n sub k. So I'm calling it X sub n sub k sub r. Now, of course, it's a subsequence of X sub n sub k, which is a subsequence of X sub n. So X sub n sub k sub r is also a subsequence of X sub n. Well, wait a minute, maybe that is important. So X sub n sub k sub r is a subsequence of X sub n. And it's a subsequence that converges. And what do we know in our hypothesis about all the convergent subsequences of X sub n? They converge to X. That's right, Chuck. So, that means X sub n sub k sub r converges to X. But X sub n sub k sub r is also, not only is it a subsequence of X sub n, but it's also a subsequence of X sub n sub k. And what did we say over here on this right-hand side of the board about X sub n sub k's? They don't get very close to X. They stay epsilon naught units away from X. So that means that X sub n sub k's sub r's, their distance from X has to be greater than or equal to epsilon naught. Because they inherit that property from the X sub n sub k's. Is being part of the X sub n sub k's. So wait a minute. You can't be, wait a minute, this is a contradiction. You can't be getting very close to X, arbitrarily close to X, if you're always staying some distance away from it. Does that make sense? Those are contradictions right there. Okay? That's a contradiction. So we must have assumed something wrong. So X sub n, what we assumed was X sub n didn't converge to X. So X sub n must converge to X. And that ends this proof. We'll stop and let everybody get a chance to write it down. I also want to stop and let everybody have a chance to catch their breath in terms of thinking about questions that they might have, and give them a chance to ask something if you have. Is there anything you'd like to ask about for this group, or anything we've covered in the last few days you'd like to ask about? Anything on your minds in terms of questions? Al?
So, I'm like slightly lost when you say that X is n takes a lot, does converge to X.
Yes.
What do we use to make that?
Okay, Dalvin, that's a very good question. So in proofs, I'm going to say something that I'm trying to be funny about to start with. Okay? So the first thing was I said, Dalvin, that's a very good question. Most people that I see that speak, so I'm a teacher, I speak. I hold an audience sometimes in class. When they're asked a question and you hear them say, that's a very good question, 99.9% of the time, that means they don't know the answer. Okay? I don't think that's a very good question. When I'm asked something I don't know, I don't like it. So I said that you asked me a good question because I know the answer. Okay? So here's the answer. But before I get to the answer, it's a very good question because of this reason. This is the reason why I think it's a good question. We want to know why The statements are true. What's the logical argument? So anybody can write down something on the board. I can write down for what's the hook, but to have understanding why it's true. So Dalvin's asking this one question. Look, we're saying we got these X events in case of R. How do we know it converges to X? Here's what we know. We were talking about the X events of K's. They were a subsequence of X events. The X events are bound. So the X events of K's are bound. The Bolzano-Weierstrass theorem says if you give me a bounded sequence, it's a subsequence, but it's a sequence. If you give me a bounded sequence, it has a convergent subsequence. So I've got a subsequence of X events of K. I call it X events of K sub R. So it's a convergent subsequence. I don't know what it converges to, okay? But it converges. But wait a minute. In the theorem that we're trying to prove, it says every convergent subsequence of X sub n, X events of K sub R is a subsequence of X events of K. But X events of K is a subsequence of X sub n. So that means X events of K sub R is a subsequence of X sub n. And in the statement that we're trying to prove, we're assuming that every convergent subsequence of X sub n converges to X. So this is a convergent subsequence of X sub n, so it's got to converge to X. So okay. That's the right thing to ask. That's the right type of question to ask, I believe. Yes, sir, Chuck?
I got a question. Why don't you apply the Bolzano-Weierstrass
Theorem to X sub n sub K.
Why don't you apply it just to X of it? Because X of it is bounded.
Right.
So then it has to have by the theorem.
Right. Because the contradiction that we're getting, so you asked a very good question, because I have an answer. Okay? So here's the reason. If we apply the Bolzano-Weierstrass theorem to X sub n, saying then it has a convergent subsequence, that's what we're saying. We're not getting a contradictory thing in that the contradiction that happens, let me turn the camera here, is that the X sub n sub k's that we're looking at, and that is a subsequence, have the property. I didn't just pick any X sub n sub k subsequence. I picked the one out there whose distance from X always stays epsilon naught away from it. Is that okay?
Yeah.
So I got to get that established first. And then I start talking about subsequence of this, which will inherit this property. Does that make sense?
Yes. Yeah.
You asked a fine thing. Listen, I want to really emphasize this to everybody, okay? One of the beautiful things about mathematics is how strong it is. You question, you look at it. Well, why did you have to do this? There's a reason. It might not be apparent when we've studied, but when mathematicians have done a good job of setting up the logical argument, they put it there for a reason. It's there because they need it. Okay? And sometimes people kind of meander around in doing proofs, but other mathematicians will look at it and say, wait a minute, we could do this shorter. We didn't have to go in this direction. And so once you see the polished proof, they got everything there for a reason. And so that's what you question. Why do we do this? Well, there's a reason. There's nothing wrong with questioning. That's the way we learn. But there's going to be a reason. So that's the answer, John.
Okay.
I hope it's okay.
Yeah.
Anybody else? Beautiful questions. That's just fantastic. That's what we're looking for. Anything about other work? Okay. Well, all right. Why? I think I should give you opportunity to ask questions all the time. I've been so anxious to get material on the board. Sometimes I forget it. But anytime you have something you want to ask about, you just raise your hand, stop and say, that's weird. What about this? How come we did this? Why is this true? You ask. Okay? My job is to tell you the answer. Okay. Well, one of the kind of lucky reasons I didn't kind of intend this to happen this way, but that stopping at that point for questions was kind of a good thing to do. It's always a good thing to do. What was really a good thing to do is that we're still going to be talking about sequences, but we're kind of changing topics. So here, what we just had was about subsequence. That was kind of the topic that we were talking about for sequence. That and monotone sequence. So that's kind of where we went. Now we're going to talk about something different. And you might think back to the definition of what it meant for a sequence to converge. Oh, yeah, that's where we got, there exists this number L that it converges to. What does it mean to converge? It means that if for each epsilon greater than 0, there exists something. What was it? A K, element of the natural numbers. Says that for all n greater than or equal to K, there's a spot, K. So from that spot on, the terms expand. The terms, their distance, that's the value x of n minus L, is going to be less than epsilon. Does that make sense? In the definition for convergence, we say convergence if there's this number L. Well, you kind of have to know what the number L is to use the definition. And that's a real detriment for the definition. So somebody's working and says, I want to show this convergence. They got to have a candidate is what I call it. Someone they'd say, a number they'd say, this converges to this. If you don't have an idea, you can't use that definition to try to prove it or disprove it. You don't have a candidate. And so, like I said, that's a detriment. So somebody said, well, how do we handle it if we have no idea what it might converge to? How do we handle it? And so here's what was come up with. It was another notion. This notion I'm about to write down has to do with something called a Cauchy sequence. So it's named after somebody. So here's the definition. We're talking about a new topic called a Cauchy sequence. So what's a Cauchy sequence? A Cauchy sequence is a sequence. We're talking about a sequence of real numbers, okay? It's a sequence, x of n. Such that for each epsilon greater than 0, there exists a k, element of that number, such that for all n and m greater than or equal to k, the absolute value of x of n minus x of m is going to be less than epsilon. That's the definition. What the heck does this mean? It doesn't have an x in it. It has x of n. It has terms of the sequence. What does this mean? Here's the idea. Let's see if we can figure it out just for a second. I'm going to tell you about it. Look, the epsilon being greater than 0 really represents the same thing it's always been representing. It represents a... Anybody know what I've been calling it? What it is? It's a distance. That's right. So we're saying that you can go to some k. What does k represent? It represents a position in the sequence. Not a term, a position in the sequence. You know, the 50th position, or whatever. The 1000th position. Such that you get to some position. And for all positions later than that, the terms in that position, their distance from each other is going to be less than epsilon. Meaning the distance from each other must be getting small. That's the idea. Audra, the idea, as you said, is that a Cauchy sequence is a sequence whose terms are eventually getting I'm going to write it down here. Getting arbitrarily close to each other. So, Megan, you know, I said we're trying to get over the deficit of the definition for convergent sequence, of having to know what it converges to. And we're doing it in this way. So here's the kind of the idea. The idea is this. Hey, look, if a sequence converges, well, it's got to get really close to a number. After some point, Dalvin, all the terms get really close to this particular number, Brad. But if they're all, after some point, really close to this particular number, they must be really close to each other. So I said, well, let's just look at the sequences that get really close to each other. And it turns out the real numbers, for sequences of real numbers, those two things are equivalent. If the sequences are getting arbitrarily close to each other, the terms of the sequence, if they're quotient, then they're going to be convergent. And if they're convergent, then they're going to be quotient. So this is a way of relating convergence to something else where we don't know, Megan, what it converges to necessarily. We just know that it converges. Is that okay? Okay. But we haven't proven that yet, that those two ideas are the same in the real number system. They're not the same everywhere, but they're the same in the real number system. And so we're going to work on that. But first, I said here's the definition. Let's give an example. What something is quotient. And I told you, it turns out that if you're convergent, you're quotient. If you're quotient, you're convergent. So let's look at something and show that it's quotient. Of course, I'm going to look at something convergent. I'm going to look at my favorite thing. My favorite sequence. Brad, what's your favorite sequence?
I don't have a favorite sequence. I like all of them equally the same.
Well, Brad, that's very kind of forward thinking for you. I'm not that politically correct. Okay, I like one better than the other. Chuck, you know what my favorite one is?
1 over n.
1 over n. So let's look at that. Is a Cauchy sequence. So Melissa, what I got to do is to make or show that the terms of the sequence eventually get arbitrarily close to each other. All right, so how do I do this? Well, it's based on the definition. That's what I'm looking at. So here's the proof. So Chuck, this is the way these proofs start. They say let epsilon be greater than 0 be given. Now, what we're looking for is we need, you know what we need? Well, that's the same thing we always were looking for. We need a k, it's a natural number. We need a spot, 6. Such that anytime you take two quantities beyond that spot, for all m and n greater than or equal to k, absolute value of x of n minus x of m is going to be less than epsilon. That's amazing. So listen, what I'm saying is if you give me this epsilon, I can find the spot. You've got to give me the epsilon. It depends on epsilon, the spot that I'll pick. But once you give me some distance, I find the spot. And from that spot on, I mean the sequence goes on forever. From that spot on, all the terms from that spot on are within epsilon distance of each other. Not just the first 70. All of them. The k plus 1 to the k plus a billion, they're within epsilon units of each other. That's what I want to show. Okay. Well, let's write down what we need in terms of what we're working with. So we want, okay, what's x of n in our particular example? It's an easy thing to answer. What's x of n? 1 over n. So we want, right here's where I'm using my framework. We want 1 over n minus, now look, don't get confused. What's x of m? Say it again, please, Olga.
1 over n.
That's correct. We want that to be less than epsilon. Now, so here what I'll do is I'll note when we have 1 over n minus 1 over n inside absolute values, I want to tell you that's the same thing as being less than or equal to the absolute value of 1 over n plus the absolute value minus 1 over n, which is equal to 1 over n plus 1 over n.
common thing to try here, Brad, that I'm not doing, but would be a normal thing to try, not beneficial, Brad, would be to get a common denominator. You know, we'd add or subtract two fractions, you get a common denominator. But if you get that, it kind of makes things more complicated out. So we don't have to do this. I just get to this. Now look, what I'm trying to do is show this guy right here is less than epsilon. If I could show something that's bigger than it is less than epsilon, then we've shown the smaller thing is less than epsilon. So if I show this guy is less than epsilon, we can check. I can do that. Why can I do it? Well, one thing we showed a long time ago is, recall, that the soup of this, the soup of 1 over n such that n double the natural numbers. I shouldn't say the soup. The nth of this is equal to, what would we say the nth of this guy was? Yeah, it's 0. And we've shown that 1 over n is a decreasing sequence. Okay. So, what that implies is there exists a k element of the natural numbers such that for all n bigger than or equal to k, 1 over n will be less than, be sandwiched in between 0 and epsilon over 2. So epsilon is a positive number. Epsilon over 2 is a positive number. Okay. Epsilon over 2 is not the infinity because that's bigger than 0. What does it mean not to be the infinity? That means it's not the greatest lower bound. If we give me something that's bigger than the greatest lower bound, then it's not a lower bound. Okay? 0 is the greatest lower bound. Something bigger than 0 is not a lower bound. So if it's not a lower bound, if epsilon over 2 is not a lower bound, there's some n such that 1 over n is less than n. But it turns out because you're decreasing sequence, really I should say there's some k such that 1 over k is less than epsilon over 2. But because you're a decreasing sequence, as long as you get beyond k, you got smaller. So 1 over n is going to be less than epsilon over 2. And you could say the same thing not only for n's, but for, what else are we talking about? What other n's? M's. 1 over whatever, once you're beyond k, is less than epsilon over 2. So, also, for all m greater than or equal to k, 0 is less than or less than 1 over m is less than epsilon over 2. So for all n and m greater than or equal to k, we have 1 over n plus 1 over n. So if I add these two smaller guys, they're less than the addition of the two bigger guys, which equal to epsilon. So that says that 1 over n minus 1 over m, which is less than or equal to 1 over n minus 1 over m, I'm sorry, plus 1 over n, is less than epsilon. And that's not true all the time, but it's true for all n and m greater than or equal to k. That's what we needed to show, because that's what the definition tells us to show for a Cauchy sequence. So that says that the sequence 1 over n, I'll get out of the way in just a second, is a Cauchy sequence. That's what we have. Well, that's how you can prove something is Cauchy. Okay. Well, now I want to prove some facts about Cauchy sequences. And what I want to go towards is that I want to work towards an if and only if statement that Cauchy and convergent mean the same. That's what I'm working towards. But we're going to piece our way towards that. So I want to list this fact first. Well, the fact I want to list is, turns out that if you're convergent, you're quotient. It's easy. It's the other way that's a little hard. This part's easy. So here's the theorem. Let x of n be a convergent sequence. Then x of n is quotient. Don't forget, Saturday, Alabama plays Miami in NIT. Everybody's excited about the NCAA men's basketball. Who cares? Alabama's in the NIT. That's what we care about. Okay. Billions of people are watching.
Something else.
Yes, that's right. They are. They're watching something else. Okay, let's do the proof of this. I said it's easy. Well, let's see. I'm trying to show something's quotient. So here, I'm going to assume again, I think I can do this directly. It's easy. So let x of n be a convergent sequence. Say, well, wait a minute. If it converges, then it has to converge to something. Let's give it a name. What should we call it? Go ahead, Chuck.
W.
You sorry thing.
Say yes. Okay. What are we trying to do? We're trying to show that x of n is quotient. We just did an example, but I don't know how you guys are. Just because somebody showed me something or told me something, it takes time. But to show that x of n is quotient, we're going to do the same process, same formatting. So Calvin, we're going to say the same thing we did before. We're going to let epsilon be greater than 0 be given. What are we looking for, Calvin? Yes, sir. What's your heart? Yes, sir. We need a k. Come on now. It's a natural number. Such that what? For all n, not just n. For all n and m. That's what it says. That's right. Greater than or equal to k. The absolute value of x of n minus x of m will be less than epsilon. That's what I'm looking to do. So I'm trying to make this distance be very small. That's what we're trying to do. I hope somebody's trying to study in this hallway. I just get louder. Teacher trying to study. But this is a library. I want to make this distance be really small. There is a distance that I know is small. What distance do I know of that's small? Let me give you a second. Let me take a second. What do I know that's small? Look up there. What are we assuming? What are we letting happen? We ain't got too many lines in the proof. What are we letting happen?
X of n.
Convergence.
Converges to x, so the distance between x of n and x is less than epsilon.
Right. That's right. After some point. That's fine. All right. That's right. So here's what I'll say. That's exactly what I'm going to start with. Since, well, Chuck, I think, I'm going to write this over here. I'm going to move the camera here. What Chuck said is exactly what we're going to work to, but it's not what we're going to say first. So just for a second, this is side work. You don't even have to write that. What we know is that we know there exists, I'm going to write this down eventually, there exists a k element natural numbers such that for all n bigger than or equal to k, x of n minus x will be less than whatever I want. Okay? I'm just going to put a box. I can make it less than any positive number you give me by going far enough along. Okay? I don't have, the thing I'm looking at, let me go back. So we got that statement. But the thing I'm looking at is to make the absolute value of x of n minus x of m be less than epsilon. I don't have an x in there. I don't have an x in here. But I could work with the x's if I had it. So what mathematicians do is we say, well, get it in there. if you need it and it's helpful to you, insert it somehow. Well, how do I insert it? Well, let's look at it. So I'm going to make this is right here be small. Well, I'll say, no, look at it. X of n minus x of m, whatever that is. That's the same thing as x of n minus x. What else am I can just do that.
Add x.
I'm going to add x. And then that isn't the quantity yet. What else I got to have? Minus
So about
x of m. There's the sum. Okay. Okay, so I'm about to move to the other board, but I want to look here for a second. Look, a lot of times when we're trying to show something was less than epsilon, we get something bigger than it. And we show the bigger guy was less than epsilon, the smaller guy would have to be less than epsilon. So, okay. What's something that's bigger than this? What could I use to get a less than or equal to? Wait a minute, what have I got? I got something, you can think of this as one quantity, plus something else inside absolute values. So the absolute value of one thing plus another thing is always less than or equal to. Okay, so you tell me what to write. I think you guys got the right idea, but you tell me what to write. How about it? Audrey, you tell me the first thing to write. Is less than or equal to?
The absolute value of x of n minus x.
Okay, and I stop there. Now, what symbol do I put next? Plus. And then what do I write? That's what it is. Is that okay? That's what that is. And what fact did we just use? How about it, Megan? Well, let's just go from there to there. Yeah, Brad said the right thing. What is it?
triangle.
Triangle inequality. That's what we're using. That's right. It came back again. Okay? So that's what I have. Wait just a second. I know, because what I wrote on that sideboard, I can make this be less than whatever I want to if I go far enough along in the sequence. But this is the same thing as this, really. You know, x of whatever minus x, the difference between x and x in the term of the sequence. Okay? So I can make this be as small as I want to by going far enough along in the sequence. But I can make this be as small as I want to by going far enough along in the sequence. How many of them do I have here? How many absolute value quantities do I have? 2 of them. So for them to add up to be less than epsilon, it'd be nice to have this one be less than, and this one be less than. Okay, so here's what I'll say. So since I can make that happen, okay? Here's how I write. So since the limit as n goes to infinity of x of n equals to x, there exists a k, element of natural numbers, such that for all n greater than or equal to k, absolute value of x of n minus x will be less than epsilon over 2. Well, I mean, it works for n bigger than k. It'll work for all m bigger than k. So for all n and m bigger than or equal to k, we have. So listen, I just want to make a complete sentence. And I want it to be a sentence that pertains to what we're trying to get. So I'm going to start off with what we have. X of n minus x of n. I had that. That's the guy of interest. That's the guy I want to show this less than epsilon. That's the guy I want to show this less than epsilon. Well, what do I know that it's less than or equal to? Well, here's what I know it's less than or equal to. I know it's less than or equal to what's written right here. But I know this is, when I go farther than k, this part is less than. And when I go farther than k, this guy for m is bigger than k. This guy is less than epsilon over 2, which is equal to epsilon. So we have what we want. So for all n bigger than n and m bigger than or equal to k, x of n minus x of m is less than epsilon. So what? What does that give me? That's the thing that is the definition of Cauchy. That's exactly right, Brad. So that says x of n is Cauchy. Wait a minute. You know, it's easy to get lost in things. What what the heck were we trying to show? We tried to show x of n was kosher. What were we working with? A convergent sequence. What did we just prove? If you're kosher, if you're convergent, you are kosher. That's all we've shown. We got to show the opposite direction too. That takes a little bit more work and a little preparatory work. We got to get going before we can get that system. We have got to build up to it. That's a little tougher. Let's do some building. Okay. Okay, so here's the build-up to help us get where we want. Here's the fact. So here's the theorem. Here's the theorem. UCLA should have never made NCAA basketball. Right. And it sure shouldn't have been win that game. But they did. The other team did something that they shouldn't have done. Go. Yeah. I made a mistake. I saw two college basketball games live. Both of them involved Alabama. And one of them involved UCLA. Alabama beat UCLA. Alabama's not good. And we beat UCLA. We don't have the transitive property in basketball. Okay? UCLA's not that good. I don't know how they win. So I'm on video saying UCLA's no good. How they won, I have no idea. They don't either. Okay, theorem. If x of n is a sequence, is kosher, then x of n is bounded. You know, we've had the conclusion is bounded before. What was it that was bounded? Convergent sequence. If you're convergent, you're bounded. And you know, the proof of if you're convergent, then you're bounded, it started off by us looking at a particular epsilon. The same thing happens here. We have the almost exact same proof. So here's the proof. We're going to let x of n be a Cauchy sequence. We want to show x of n is bounded. Show these bounded. I've forgotten how to do it. I have. But I know what it's going to involve. So here's what I'm going to do. I'm going to let epsilon equal to 1 be given. Since x of n, I know, is kosher, there exists a k element after numbers. So I'm giving you this specific positive number. Such that what? For all m and n bigger than or equal to k? We're almost done. We're going to stop in just a second. 1 more minute. That's it. For all n and m bigger than or equal to k, what can I say? I know x of n is Cauchy, so I can write down that x of n minus inside absolute values is less than, which is what in this case? 1. That's what I got. All right, I want to go to the crux. I want to go 30 more seconds to the real heart of the proof. And then we'll start there again next time, finish it off. Let's give you something to salivate over for next time. You're eager to come back on Monday because of how we're going to finish this off. But here's the idea. What this says then, it says for all n and m greater than or equal to k, we have this, okay? So look, I mean, I can break this down into a problem that doesn't involve absolute values, and then reintroduce absolute values by using the property that we had before. And that's what the convergence implies boundedness had in it, okay? That's what it is. But the problem is that it's going to involve x sub n. So I'm going to bound x sub n by having something on the right-hand side and the left-hand side that has x sub m. That's no good. That's no good, because the n and m are moving. Is that okay with everybody? So what I'd like is to work with something. I want to keep x sub n's involved. I'm going to let them move. But I'd like, instead of x sub m's, I'd like to replace them with something that doesn't move. Well, look, we got a fixed number up there, even though it's arbitrary. The fixed number is k. It's arbitrary. I don't know what k is, but it's so fixed. So for all n bigger than or equal to k, x sub n minus x sub k. So x sub k isn't changing. It's x sub k. That's less than 1. And it's working with that guy right there that we're going to be able to get what we want. And we'll start up there next time. Okay? So we're not going to finish the proof today. I know you're dying to see how it ends, but we'll just have to wait. It's like a cliffhanger on TV shows I used to watch all the time. Thank you very much for your time and patience.